Hello, welcome to lecture 4. Today I am going to talk about principle of mathematical induction. This is mathematics for class 11 chapter 4 based on NCERT syllabus. My name is Sangam Banerjee and my details are given below. So today I am going to talk about the principle of mathematical induction. Actually this subject has been dealt in class 9 and 10th elaborately. I would request students to go back to 9th and 10th for the sake of completeness. So suppose there is a given statement P of n where n is some natural number such that the statement is true for n equal to 1. So if I substitute n equal to 1 and I find the statement is true, that is P of 1 is true, and if the statement is true for n equal to k, which is given to you where k is some positive integer, then the statement is also true for n equal to k plus 1, that is the truth of P of k implies the truth of P of k plus 1. So it will have the same form except you substitute n to n plus 1 and you will have the similar form. We will see this as we go along. Of course, it is not necessary always to prove by induction. Some direct method is also there. So let me introduce first how you do a direct method, and then of course sometime induction method helps. So let us prove without mathematical induction some of them so that you will understand what I am trying to say. So here I have written 1 equal to 1 square equal to 1 and 4 equal to 2 square, that is 1 plus 3. 9 is 3 square, that is 1 plus 3 plus 5, that is 5 plus 3, 8 plus 1, 9. So here you see there is a pattern, that is for the nth term the number will be 2n minus 1. So here you have how many terms? 4 terms. So 2 into 4 is 8 minus 1, the last term will be 7. Okay, so this number will be always 2n minus 1. So if you have 3 terms, 2 into 3, 6 minus 1 is 5. Here 2 terms, 2 into 2 minus 1 is 3. So thus one can write P of n is equal to 1 plus 3 plus 5 plus up to 2n minus 1 term, that is nothing but equal to n square. So here I have elaborated it, that is 2 into 1 minus 1 is 1, 2 into 2 minus 1 is 3. So it's same thing what I have written. And this thing also can be expressed that summation of this symbol is called the summation of n equal to 1 to n, 2n minus 1. That is this last term if you take it and if you sum it, that is you will have n equal to 1, that is 2 into 1 minus 1 is 1, 2 2s are 4 minus 1 3. So 1 plus 3 plus 5 up to n terms if you go. If you take a summation of it, it will be 2 times n into n plus 1 by 2 minus n, and this we will derive in the next slide. So these two I write it here, and summation over n equal to 1 to n of n will be n into n plus 1 by 2, and summation of 1, that is n times, so it will be n. We will see it in the next few slides. That is equal to, if I simplify it, this is 2 and 2 get cancelled, n square plus n minus n is n square. So as we discussed in our previous slide, that sum of this is 1 plus 2 plus 3, that summation over n, where n goes from 1 to n. I can also write this s, I will invert it, and this n I will bring it here, then n minus 1 and so on in a reverse order if I write. And we know that s is whatever is written here, I have written back here. So now I add this s and this s, so I will get 2s and n plus 1, then n minus 1 plus 2 will be again n plus 1. You go on till the last term n plus 1 again. So how many times n plus 1 you have? N times you will have n plus 1. So I can write n times of n plus 1, and so this summation s, you bring this 2 down. So this summation of 1 plus 2 plus 3 up to n is n into n plus 1 by 2. This you can prove by induction also. We will see how to prove by induction also. And this is not the induction method, this is a direct method. So some more we will do some direct method. As I said that I will show you how to prove this. So there is a trick. If you want to prove summation over p, so I always take p minus 1 the whole square. And suppose you want to know the summation of p square, then I will take p minus 1 the whole cube. We'll see as we proceed. So now let us use this trick, that p minus 1 the whole square we know is p square minus 2p plus 1. I rearrange it. I bring this p minus 1 the whole square this side. So I have p square minus p minus 1 the whole square, and this 2p I bring it in the left hand side from right, so it becomes plus, and this plus 1 also you bring it, it becomes minus. So this is by rearranging. This is simple. By now you should be expert how to rearrange this thing. So now I can take the sum over p from 1 to n. So I now take summation over p square, so then minus it is here, summation over p equal to 1 to n, p minus 1 the whole square, this summation over p. Here also I take summation over p, and here also I take p equal to 1 to n. This summation you will notice that there is no p involved. So p equal to 1 is 1, p equal to 2 is also 1, p equal to 3 is also, so 1 plus 1 plus 1 up to n times. So this will be n here. This is the quantity which we have to evaluate, and we know that this is p square, and then p minus 1 the whole square. So if I subtract this from this, I will only left with 1 n square. So I write this 1 n square. If it is too fast, just pause and think about it, what I'm saying. Now this is the quantity which I want to evaluate. So I take this minus n to this side. So this quantity here is nothing but n square plus n, and n square plus n is n into n plus 1, and this 2 which is there in front of this summation, I bring it down. So summation over this quantity becomes n into n plus 1 by 2 is same thing what we have done here. So as I said that if you have p square, if you want to do, then you take p minus 1 the whole cube. And now suppose you want to know the summation of pq, then you take p minus 1 the whole 4. So you can, this is a trick which you have to remember. Now let us come back to, we want to find the summation over p square. Okay. Earlier we found summation of p. What do you mean by summation of p square? That is 1 square plus 2 square plus 3 square up to n square. Okay, this means I may be going with pretty fast, but this all we have dealt in class 9th and 10th. So by now I think you should be knowing what these symbols mean. So now let us continue this p minus 1 the whole square. I can expand it like this, which we have done in our lower classes. Pq minus 3p square plus 3p minus 1. This I am sure you should by knowing it. So now I rearrange this. I get this p minus 1 the whole cube to the right hand side, so it becomes negative here, and all this quantity I get it to left hand side, so 3p square minus 3p plus 1. Now I will take the summation over p from 1 to n. So I write here 3 summation over p square, then minus 3 summation over p, then summation over 1, then here summation over p cube, and summation over p minus 1 the whole. So this is a quantity which I want to know. So this is a quantity which I have derived here, that is n into n plus 1 by 2. And as I said earlier, the summation over 1 from p equal to 1 to n is n, which it is very obvious. 1 plus 1 plus 1 up to n time will be n. And then this is your p cube minus p minus 1 the whole cube. So what will be remaining? Only n cube will be remaining, because this summation will have 1 cube plus 2 cube plus 3 cube up to n cube, and this one will get terminated at n minus 1 the whole cube. This term will have one term less than this, so n cube will remain here, rest of them will get cancelled, so you will have n cube here. Now it is very simple. Now this simple algebra, so I get, because I want to know this quantity, I get again this one from left hand side to right hand side. So here I have got it, this minus become plus, and this plus n become minus n, and I do simple algebra here, that is n cube minus n, I can write n as common, so that is n into n square minus 1. So this quantity again I write it here, because this n square minus 1 I can write at a square minus b square is a minus b times a plus b. So I have written a minus b times a plus b. So n into n plus 1. So these all we have discussed in my last lecture also, in the trigonometric lecture also we have done such kind of stuffs. So now you cross multiply it, this 2 will come here. So you can write this divide by 2. So now you simplify this further, because this is n into n plus 1, you take it common here. So you are remaining with 3 plus 2 times n minus 1. Now this 3 plus 2 n minus 1 is, this 3 minus 2 is 1. So this is your 2n plus 1. So please pause and see whether I have done it correctly. And this is divided by 6. Because now you bring this 3 to right hand side, that means it will come from numerator to denominator. So 3 into 2 is 6, and this 2 is common here, because I have multiplied these 2 here. Okay, so 2 is common everywhere, so 3 into 2 is 6. So you have this n into n plus 1. So this is a formula for summation over p square from p going from 1 to n, that is 1 square plus 2 square plus 3 square up to n square is nothing but n into n plus 1. So if you are given up to 1 square plus 2 square plus 3 square plus 4 square, then you write 4 into 4 plus 1 into 4 into 2, 8 plus 1, 9, you multiply it, the summation will be your summation of for p equal to 1 to 4. So you can just take paper and pencil and see whether you get similar answer. Now let us do proof by induction, that proof that p of n, which we have done earlier, 1 plus 3 plus 5 plus 7, we did earlier by direct method, but now let us do the same thing using induction. So we know that p of 1, this is a basic step, as I said, that p of 1 is true. P of 1 is equal to 1 square, that is p1 is true. Okay, so if you take the first term is equal to 1 square, because you have given this formula 1 square, so this is true. Now I assume that this is also true, okay, for all n. So if it is true for all n, then it should be true for n plus 1 also. So let us suppose that pk is true. See, this is a dummy variable. I'm writing a separate alphabet here instead of n. So it is immaterial. You can, so just to keep a track of it. So p of k is true for some positive integer k. That is, this equation is true. So as I said, instead of n, I'm writing k. That this is true, I know. Now we need to prove that p of k plus 1 is also true. So what I do is I write this 1 plus 3 plus 5, and this I substitute n as k plus 1 and this also as k plus 1. So here I have written here that 2k minus 1, and this is, as I said, I am substituting n as k. So this k, you have here k plus 1 minus 1. So this is an extra term which I have taken. Now this term is nothing but, if I take it, so we know that up to here is k square, that is n square here, plus 2k plus 1 which I have taken, 2k plus 1 minus 2, that's 2 minus 1 is 1, so 2k plus 1. So now if I add all this, I will get k plus 1 the whole square, that is k square plus 2k plus 1. Okay, so it is having the same form. This is your, instead of n, I am writing n plus 1 the whole square. If I take one more extra term, okay, if I substitute this n to n plus 1 by adding one more, I will get the same form. Therefore p of k plus 1 is true, and hence pn is true for all natural number n. So if it is not getting clear to you, please pause it and see this argument. I'm sure if you go through it once more on your own, you will understand what I'm trying to say. Now we will prove without mathematical induction what we have proved in our earlier slide. 1 plus 2 square plus 3 square is this. There's another way. As I say, that there may not be a single method in mathematics to solve. There may be various methods by which you can solve, but everything has to be logical. So here is one trick using number triangle to prove this one. So this is for you all to know that how same problem can be solved in various methods. So let us use this new way of doing it. So you construct a triangle and write 1 and then 2, that is 4, 2 plus 2 is 4, then 3 3s, 3 3 3, that is 9. So this is 1 square plus 2 square plus 3 square. So this I can always write as summation over I square, this one up to n. So there are n of this n, so that is n into n will be n square. Okay, so 1 square plus 2 square plus 3 square is 9, 4 square is 16. So I make this kind of a triangle, and now I take same triangle and I rotate it, and I bring this one here. Okay, so if I bring this one here, this n which is here will go here, and similarly I rotate one more time and this one will come here. So this n which was here, now it will come here. So this is a trick which I am going to show how to prove this also. This is a very interesting proof which I like it, so I thought I will tell you, and this was discussed in class 9th also, so it is okay for you to know now again. So here again you have 3 of them, 3 of summation of I square. This is 1 square plus 2 square plus 3 square. So you have 3 of them because it's same thing which you have rotated. So now if I add them, 1 plus n, it is 2n plus 1. Then again you have 2, then n minus 1 here, and n here I have written 2 plus n minus 1 plus n. This is your 2n plus 1. So again you have 2n plus 1, and similarly 2n and n minus 1, again you will have 2n plus 1. So similarly you can build this kind of a pyramidal structure of 2n plus 1, and here you have n times 2n plus 1. Okay, this 1 2 3 up to n times. So now if we take a summation of it, that is 2n plus 1 is common, is 1 time, then 2n plus 1 is 2 times, then 3 times if I write it here. So this I know that 1 plus 2 plus 3 which we have done it is n into n plus 1 by 2. So if I write here n into n plus 1 by 2 and then 2n plus 1 here, but you have here 3, so I have to bring this 3 here. So 3 into 2 will get 6. So I am doing it very quickly, but you should able to understand it, because if I do every step, then you will not think. Now let us prove the earlier one by mathematical induction. Okay, so how do you do it? 1 square plus 2 square, this we have to prove it. What we have done without induction with the direct method. Previously we did with direct method, and another directly we did using the triangular concept. Okay, so now what is the basic step? Basic step is for n equal to 1, p1 is equal to 1, because of course this is the first term, only one term, p1. So 1 square is 1, so this is true. 1 into, see here, 1 into 1. So if I take it, this is 2, then this is 2 into 1 plus 1, that is 3. 3 into 2, 6. 6 divided by 6 is 1. So this is true. So for the first term, this equation is valid. So now I assume that this is valid also for whatever is given to you. So here assume that pk. So as I said earlier, let us change the variable to k here. It is immaterial. Assume that p of k is true for some positive integer. That is, this up to k square is k into k plus 1 into 2k plus 1 by 6. So if I assume this to be true, then of course we shall now prove that p of k plus 1 is also true. So I have to add this k square up to here, then plus one more term k plus 1 the whole square. So I will have here, for this one I know this is given to you here, and plus k plus 1 the whole square. So now let us simplify and get this two term and make it one term. So then I do cross multiplication, multiply by 6, and of course this 6 is there, divide by 6. So this is 6 and this is multiply by 6, and then you take your k plus 1 is common, this is k plus 1 and this k plus 1 is common. So now since I have taken k plus 1 as common, so here is remaining is k times 2k plus 1 I write here, and your 6 of k plus 1 instead of square I only take 1 because I have taken this k plus 1 common, divide by 6. So here again I simplify this, I write k plus 1 common. So this is your 2k square plus here is your k plus 6k is 7k, and then you have 6 into 1 is 6. Just pause it and go through what I am doing, so that if I have made any mistake you should able to correct it. So now again I take k plus 1 the common, same thing, and I can write as, I will factorize it, which we have studied in lower class. So I have splitted this middle term into these two terms. Then see that how I have factorized here. This whole, this in the red square bracket is k plus 2 into 2k plus 1. Here I have done it. Just go through it. And now I have just simply rearranged this. This is k plus 2. I have written k plus 1 is k plus 2. And this is 2k plus 1. So this is your 2 times 1 is 2 plus 1 is 3. So this I have just rearranged it here so that it should look this form. Instead of n, you should have n plus 1 or k plus 1, then here also k plus 1, here also k plus 1, and we are really getting, this is k plus 1 here and this is k plus 1 here. Here is twice of k plus 1. So that means it is true for the k plus 1 also. Thus p of k plus 1 is true whenever pk is true. If this pk is true, then p of k plus 1 is also true. Instead of k I can write k plus 1, or instead of n I can write n plus 1. Here k is a dummy variable. What do you mean by dummy variable? It's immaterial of what you write, what alphabet. Instead of k I could have written m, q, but all should be same. Q, here also q. Okay, so that means it is a dummy variable. So thus pk plus 1 is true whenever pk is true. So hence from the principle of mathematical induction, the statement p of n is true for all natural number n. Okay, so pause it and again you go through it what I have said. Now let us do exercise 4.1, prove by mathematical induction. This is again taken from your textbook. So problem 1 plus 3 square up to 3 to the power n minus 1 is nothing but, so if you don't have to add here, this is a formula given for such kind of a summation. So how do you prove this is true? So for n equal to 1, this is 1. So I put here n equal to 1 here. 3 minus 1 is 2. 2 divided by 2 is 1. So it is correct. So for n equal to 1, only this term if I take, this formula is valid. And for n, of course, this formula, the given formula is valid. Now for n plus 1, I write 3 to the power n plus 1 here. Okay, minus 1 by 2. I should get that. So how do I get that? So n plus 1 means this, and here 3, this is 3 to the power n plus 1. So n plus 1 minus 1 will get cancelled. So you'll have 3 to the power n. So plus 3 to the power n I added here. And up to here the summation is this. So now I just simplify it. This is 3 to the power n into 2. Here I have done it. And this now, this is a cross multiplication. So divided by 2. So now I just simplify this. So here we have 2 times 3 to the power n plus 1 more 3 to the power n. You're adding it. So you have 3 times 3 to the power n is 3 to the power n plus 1. And this minus 1 is here divided by 2. So you see here, so this is true for n plus 1 also. This have a same form. So now the second problem, 1 cube plus 2 cube plus n cube. I am doing it very briefly. So kindly do all the steps right properly. Okay, this is just I am doing it in the margin to show that these are not so difficult. So this summation of all this cube is nothing but n in times n plus 1 divided by 2 the whole square. Okay, so you can do this kind of thing by direct method also, but sometimes too lengthy, but induction method helps you. So how it helps you? So again p1 is true because this 1, n equal to 1 is 1 into 1 plus 1 is 2 into 1, 2 by 2 is 1, 1 square is 1. So this is true. So then of course this is true because this is a given thing. that they want you to say prove that this is true, so you assume that it is true. Now you add n plus 1 term. So if I add n plus 1 term, so this whole term is this term which is given to you plus n plus 1 the whole cube. So again I do here cross multiplication. The 2 square is become 4. So you take this 4 and just simplify it. Take this n plus 1 the whole square as common here. So you will left with n plus 1 only. So 4 times n plus 1 you will get, and this is your n square here. So this is n square. This is the total square. Okay. So this n square from here you get it, and then you have 4 of n plus 1 divided by 4. Okay. This 2 square is this 4. So now you have this as n plus 1 the whole square. This is n plus 1, and n plus 1 plus 1 is n plus 2. So it has the same form for n plus 1. So by induction method we say that it is. So similarly here 1 plus 2, this is then 1 divided by 1 plus 2 plus 3. So this is what this is equal to 2n divided by n plus 1. So if you add all of them, you will get this. Okay, whatever the value of n is. So if n is 1, it is 2 into 1, 1 plus 1, 2, 2, 2 is 1. So it is true for P1. So now let us do this one. So here again I have written here I have taken this 2n by n plus 1, and then I have added one more n plus 1 here. Okay, so this term has been added. So now I can club this to get this as 2 times n plus 1 divided by n plus 2. So now I again club these two things, this plus 2 only one formula. So here this is same thing I have repeated here, and this is 1, and this denominator is nothing but, see here you have n plus 1 up to n plus 1 term. So we know that up to n was n into n plus 1 by 2, but when you have n plus 1 term, so I write n plus 1, and that n plus 1 will be 2 divided by 2. Okay, just go back and you just substitute this value here. Now you simply cross multiply and take this 2 by n plus 1 as common. So you have n, then 1 by n plus 2. So now again here you do cross multiplication. So you will get n plus 2 times n plus 1 will be n plus 1 the whole square. Just do it in your writing pad, divided by n plus 2, and this n plus 1 will get cancelled with one of them. So you will have here 2 of n plus 1 divided by n plus 2. So what I said here, 2 of n plus 1 times n plus 1 plus 1 is n plus 2. So it is true for n plus 1 also. Please complete this. I have given you how to go about doing it. You have to write each of the step, okay? The basic step, then say this is by. So I have not written the words or the sentences which you have to add. And similarly here, a plus ar square up to ar to the power n minus 1 is. So this is the formula. If you have to add this, you should get this one. So let us prove by induction. So here I am not writing all this p1 is 2 and all. You can definitely write for n equal to 1, r minus 1, r minus 1. So a. You should write all this statement. I am just giving you briefly so that it is easy for you to understand and then later on elaborate when you have been asked to solve this problem. So here again you've taken up to here, then you add one more term, n plus 1. N plus 1 minus 1 is only n. So here I have added here and I have got n. So now I club this too because I want a single formula here, means of this form, not single formula but actually of this form we should get it. That is, when you take n plus 1 term, you should have here n plus 1 also. Okay, so I have taken one more term, n plus 1 term, and we just go through this and we will see that we will again get here a times r to the power n plus 1 minus 1 divided by. So as I said here, you should get this. So this is also valid. So by mathematical induction, you can say that if it is valid for 1 and it's valid for n, then it is valid for n plus 1 also. And this is a direct method. It's 1 plus r square plus same thing which I have written. You call it S. This is what we have to find out. So what I do is multiply each of the term by r. So r into 1 is r square, r cube. So I get it here. Since I'm multiplying by r, so this last term will become rn. So now if I subtract this s from this rs, s I keep it common, that is r minus 1 times s, and this, if I cancel all these things, I will have r to the power n minus 1 here. So r to the power n minus 1, and as I said here, s is common, so r minus minus 1 which is here, I bring it here. And this I have done in class 9 also. So please go through my class 9 lecture note. Now problem 18, that is 1 plus 2 plus 3 up to n is less than 1 by 8 times 2n plus 1 the whole square. So how do we prove by induction? I substitute n equal to 1 first, as I said. This is the basic step. So here 1 times 1 plus 1 is 2. 2 into 1 is 2 divided by 2 is 1. So I have 1 here. And here n equal to 1 means 2 plus 1 is 3. 3 square is 9. 9 by 8. So it is true. So now to prove this is true, so I have to add one more term, that is n plus 1. So I know that the sum of this up to n is n into n plus 1 by 2, which we have proved earlier, plus the addition term n plus 1. So now we have to prove that this term is less than this. We have been told is 1 by 8 times 2n plus 1 the whole square, and this plus n plus 1. So we have to prove this one. So let us first prove what is the value of left hand side, and I call this as right hand side. Okay. So what is left hand side? Left hand side is n square plus n plus 2n plus 2, which I have written here, divided by 2, but I want 8 here. So I multiply by 4 all the term, and if I add, I will get 4n square plus 12n plus 8 by 8. Just go through, this is a very simple thing. And similarly, the right hand side is your this one, that is 2n plus 1 the whole square plus I cross multiply it divided by 8, I get this. And so if I simplify this, I will get 4n square plus 12n plus 9. So you see, this is 8 here, this is 9. So your left hand side is less than right hand side. So this is true for n plus 1 also. So by mathematical induction, I can say that this is a correct statement. So this is another problem, that is 41 to the power n minus 14 to the power n is a multiple of 27. So this statement is given to you. So this is a true statement or not, we have to find out. So for n equal to 1, 41 minus 14 is your 27. So this is a multiple of, for P1 is true. Okay, for n equal to 1 is true because 41 minus 14. Now this is given to you. So this, the statement I have written in mathematical form, 41 to the power n minus 14 is 27, multiple of 27, some multiple of this is d, some number. So for n plus 1, I write again 41 to the power n plus 1, this becomes n plus 1 minus 14 to the power n plus 1. I can simplify this again, I just minus and plus, same thing, 41 into 14 to the power n. This is, I just subtract and add these two terms, it is immaterial, it's cancelled, and this minus 14 to the power n. Now I take 41 common, so I have 41 to the power n, that means, and here it is 1, so n plus 1, this is the term. And since 41 I have taken common, so only this term is remaining, so I write 14 to the power n. Similarly, here I have taken 14 to the power n as common, so 41, and here is 41 to the power n plus 1, so n I have taken outside, so only 14 to the power 1. So again, this is your given here 27d, and this is your 27. So this thing 27 is a common, so it is a multiple of 27. So it is true. Okay. So by induction, this kind of problem can also be solved. So I think I will stop here. More or less, I think you have understood what proof by mathematical induction means. So thank you and see you in next lecture.